Hi everyone, welcome to the demo on transport cost optimization by YASH Technologies. Today we'll be discussing regarding a product that can be used across logistics and transport cost optimization problems faced by the industry. Currently, third-party logistics providers and manufacturing enterprises are competing worldwide through better transport optimization strategies to reduce costs while achieving high standard of deliveries. Transport and logistics optimization is currently the biggest opportunity for most companies in order to attain significant reduction in operational costs. 3PL providers and other logistics providers that depend on conventional scheduling methods can save up to 10 to 40% on operational costs by improving decisions such as the optimal selection of the routes and picks. We present YASH data science driven approach and methodology to transport cost optimization through advanced heuristic optimization methods for handling large-scale data. So we start with an introduction to the platform. As we already discussed, this particular platform is for transport cost optimization problems that is being faced across logistics and operational business that is being witnessed in the industry today. Just to give an overview of the business problem, in an ideal vehicle routing problem, let that be in the manufacturing or 3PL industry, the goods that are loaded from depot or let's say from pickup points are being transported to the customer delivery locations. When you have multiple delivery locations that can possibly go from a particular pickup point or a depot, there's a challenge in making a decision on which customer should be delivered first, second customer should be who, the third could be who. This particular decision provides a problem for the delivery optimization problems that are caused in the industry today. So the whole idea behind the platform that has been developed over here is to analyze multiple possible routes that can happen in a particular possible scenario and identifying the most optimal route in terms of cost as well as distance. So that is the overall business overview and the how the approach has been developed in a very broad level. Now coming to the data points, we have collected real data on the basis of the depots, customers, truck capacity, truck partition 1 capacity, truck partition 2 capacity, average speed of truck, and the cost. Now, if you observe, you will observe here that the data has been collected particularly for the manufacturing industry over here, and the prototype which you are showing over here is of a sample data for the analysis and the demonstration purpose. So once these data points are collected, we have data frames for separate this thing. Then we create an objective function. The objective function is the business objective that we have, which is to minimize the transportation cost through optimal route allocation of trucks, where the aggregate distance traveled by all the trucks in a day is minimal. So this is the objective function that we have created, and mathematically we have explained over here is to minimize the total distance in terms of cost and other functions that we have developed over here, the factors that we have. And according to that particular function, we are describing to minimize that particular objective. With respect to the constraints, that is subject to the constraints such as the total demand for the constrained delivery days availed. That is, if we have a particular number of demand deliveries that we need to meet in a particular day, that should be first of all delivered. Second, all the customer delivery locations should be allocated in the selected routes. So if you have considered a particular route combination for different customers, then all the customers should be able to deliver in that particular day in the limited time that we have been allocated for a particular truck or a driver. Total demand to be delivered in a route should be less than or equal to the truck capacity. Individual demand of the two products to be delivered in the route should be less than or equal to the truck partition capacity. Aggregation of start time, traveling time, and quality check time lie between the delivery interval of customers. Each depot can load a fixed number of trucks at any particular given point in time. So these all act as the constraints over here, and we need to find out the most optimized routes, keeping these constraints in the algorithm that we have developed over here. Now, the benefits we have already discussed. It reduces transportation costs, it improves the utility of the assets, resource allocation, and also it reduces the warehouse receiving costs and so on. Also on an environmental level, we're talking about reducing the carbon emission because the less distance traveled in a very minute level. Before proceeding to the product, just to give an idea about the platform that we are showing here as prototype, we have developed the algorithm on R, which could be developed on other platforms depending on the delivery requirement, and we are showing it on R Shiny over here. Now moving to the data part, as you can notice here, we can take the data in a CSV format, or we can directly call the data from an SAP platform. For the demo purpose, we are showing it over in a CSV format that we have collected the data. So we browse the data, we collect that particular demand file which we have, and then when we browse it here and browse, we take the customer in different locations. Once these two data sets are imported to the our platform, we can analyze this data and we can apply the algorithms that have been developed to get the optimized routes. Just to take you, could be possible in one particular combination, and the max that can occur. So of course, there cannot be thousands of them together or hundreds of them in one route itself. So there's a range, max range and a min range, which is attached to each of it. Now we go to the time window, which is basically, it's not shown here, it's internally how it works. Once the data has been extracted, then we apply some constraints, different constraints to it. So for the second constraint, what we have over is the time window constraint. The first constraint has been allocated, which is demand constraint. That is a min demand and the max demand that can come in a possible route. Then we go to the time window constraint. That is basically explains when does the customer want the product to be delivered. So that is what is being put as a constraint over here. For example, if the customer says that, okay, I need the requirement between 6 o'clock and 8 o'clock in the evening, then according to that, this particular constraint has been added. So the C15 or the customer 9 or the customer 2, according to that, this particular time window has been added, and this constraint, according to it, different routes been allocated. Now we move to the cost estimation. That is basically with respect to each of the route that we have generated. So you can see there are thousands of different routes that are possible routes that are still there. Out of these routes, what is the cost that would occur in terms of the movement of the truck from one location to another location from the depot once it has started? That can be possible between these customers. You might observe that there are combinations sometimes of C1. That is because the total demand is 11 tons in the analysis that we have carried out. So that crosses up to at least minimal requirement of one truck in this case. According to the demand, according to the requirement, this would definitely change. And if the demand is less than 2 or 3, then multiple this can come up. Also, there's another constraint is the total distance. So one truck can go and deliver to one customer, and it can come back and it can deliver to another customer. So different combinations we get over here depending on the kind of data that we talk about. The lower bound and upper bound, what we essentially talk is in terms of time, but in decimal units. And when 4.23 can be converted into hours, which it says that what is the time that a particular customer's truck should be loaded. So we give information on that also. For example, if the customer needs delivery between 10 o'clock in the morning and 2 o'clock in the afternoon, 2 p.m., then the delivery, considering the total time to travel from the depot to him is, let's say, 4 hours, then the time that he should start is before 6 o'clock. The loading time should be before 6 o'clock. So this particular range talks about that. At what range, at what particular boundary range or the time range that we have, that the particular load should start occurring in a particular truck. So that is what being shown over here. Once this is done, we move to the detailed report of it, which is basically the final schedule that you have. This is the final output a user gets in terms of managing his deliveries in a particular day. So as you can observe here, different combinations of different routes have been provided here, and it says that, okay, for the truck number, this particular number, or truck number 2357, we have the route of combination of C8 and C11, and it should start at 11:20. Loading time should be at 10:30, and so because we give a 45 minutes of loading time in between, and the total demand that will be delivered that day will be 12, and total travel time in terms of decimal units a year, and the cost that would incur. So all these analysis and the final output is being provided away, which could be downloaded in a CSV format or to another visualization platform which that will require. So that is being shown over here. And once we get the final output, the last output that we have, we move to this particular output that has been generated over here is used for the final decision. And this would be required for further optimization in real time if required. So this is the final part of it in terms of live tracking. We have also generated KPIs for analyzing the total demand as well as delay. So this is the final part of it, where you can observe that we have the aggregate delay variance. That is basically for each of the region, what is the variance that has occurred particularly, and aggregate is what. So we get the variance. Or some days there was a 5% up to 5%, 4% delay in terms of negatively. Some days it went to positive. So this variance has been analyzed over a period of time, which will help us in identifying where exactly the delays are occurring, on what route, on which driver or a particular truck, and what are the factors that are contributing to the delay that occurs in a particular period of time that we talk about. So that analysis is being carried out for the decision maker to understand exactly where the delay has been happening due to what reason over here. So that has been further analyzed with respect to different factors that we have. For example, you can see seasonality. During every particular month time, we do observe seasonality has a huge impact. Let's say during monsoon season, there's a delay occurring more. And so that has been identified through seasonality factors. Also other factors such as truck driver, time, rural roads, metro roads, highway roads. How much of the percentage of the total roads being covered by the truck is having highway roads? And that has been taken as a data point over here, and that has been put as a factor to analyze the impact of these factors on the total delay. And also we give a descriptive analysis on the historical data to understand by which truck the particular delay has occurred the most, and also with respect to which driver. So with that, this particular platform provides information on the overall the approach to this thing, and also to the approach that we have developed, and what is the final output, and how it could be utilized for logistics and transport cost optimization. That we come to an end to this demo, and so thank you.